Good morning from our side. I will present a study which has been conducted by myself, Michael Felix, who is here, and our colleague Benoit Figuet, who cannot be here today, but he is quite a large contributor to the traffic library indeed. Before I start in the following, I will always abbreviate this term alternative ground propulsion system as AGPS. So just having said that before starting. So most probably some of you know this document shown here, that's Flight Path 2050. That's Europe's vision where challenges or future challenges in the areas of competitiveness, performance, and sustainability for aviation are stated. And to tackle these challenges, a number of goals are specified, and one of these goals is, quote, aircraft movements are emission-free when taxiing. So in the following 10-15 minutes, we go through the question of whether this goal is realistic and whether we can find answers using OSN data which provide like intel to this question. But before really starting, I have to give you a short overview on what taxi movements are. So on an airport, you basically have two types of taxi movements. One is of arriving aircraft. They land and they taxi to a stand that's shown here in green. And of course, the other one is the other way around, which is shown in blue. That's aircraft which are parked on a stand and then subsequently take off. So in the following, I only speak about the blue trajectories, meaning departing trajectories. So how does such a taxi procedure of a departing aircraft look like? I made a little description. So first, if the aircraft is parked on a so-called nose-in, push-out stand, it needs a pushback. That's nothing but like a car pushing back the aircraft onto a taxi bay, because aircraft basically cannot move backwards. Some can, but most commercial airplanes cannot. After that, pilots start up their engines. That's called the main engine start. And once the engines are started up, the so-called warm-up period starts. That's a period of time the engines are required to run in idle before pilots are allowed to apply takeoff thrust. Both main engine start and warm-up periods are engine related. So there are no fixed values. Some aircraft take longer, others take shorter. During the warm-up period, however, pilots are allowed to taxi. So they can taxi during this warm-up period to the runway, where at some point they line up. That's the process of entering the runway, and then they finally take off. If you look at the image on the left, top left, we see that the taxi process has basically three emitters. Let's put it that way. One being, of course, that's quite obvious, the engines of the aircraft. Then also we have the so-called APU, which is the auxiliary power unit. That's a small little engine in the aircraft, which supplies the aircraft with energy as long as the engines are not running. And of course, if we have a pushback, of course, the pushback tug also requires energy, and there are emissions from the pushback tug. So if we now think about emission-free taxiing, we have basically two options at our hand. On the one hand, we have so-called operational measures. These are usually available to airports and air traffic control. For instance, air traffic control, and they do that they do that today. They do active queue management. So the goal is to only release aircraft or to allow aircraft to start up engines if capacity permits for a takeoff, or they allow for direct taxi routes, especially on large aerodromes. On the other hand, we have technical measures at our disposal, and here the AGPS come into play. And here we have to differentiate between the so-called internal AGPS, that's nothing but usually an electric motor fitted in either the main engine, the main gear, or the nose wheel gear, or on the other hand, we have so-called external AGPS, and that's nothing but a pushback tug, basically. So in the following, we focus exclusively on this external AGPS for sake of simplicity. So knowing that, we can now ask ourselves, so which part of the taxi process can these AGPS be used? And basically, it's during the taxi out phase, because we cannot substitute main engine start. We need that. We need the engines running for takeoff, and we cannot substitute the warm-up period. We need the engines to be warmed up. So what we can substitute is, to a certain extent, of course, is the taxi out phase. And within this taxi out phase, external AGPS could be used. And now our research question was to find out or to show ways of how OSN data can be used to determine what the fuel saving potential for an airport is or could be if such external AGPS are used. So let's have a look at the methodology which we applied in order to give answers to this question. And the methodology is basically three-stepped. First, we had to find ways to determine the duration of taxi for a given flight, meaning a given surface trajectory of an aircraft. Then we had to find ways to determine its fuel consumption during taxiing. And if we can do 1 and 2, we had to apply these methods to like a large number of trajectories in order to find out what the fuel saving potential for an entire airport is, just to have stable results. So let's start with the taxi duration. We defined taxi duration as the interval between the start taxi time, the time the aircraft starts taxiing, and the time the aircraft lines up on the runway. So that's what we defined as the taxi duration. And the lineup time we determined by first checking on which runway the aircraft actually takes off. And to do that, we proposed a little update to the existing method on traffic by implementing a filter which filters the initial climb trajectory for a flight and then checks which runway aligns best of an airport to this initial climb segment. So knowing the takeoff runway, we then determined the lineup time by adding a buffer geometry around this runway. That's nothing but a rectangular box. And we checked when the aircraft first enters this rectangular box that's shown here in red. So that's how we determined the lineup time. And secondly, to determine start taxi time, we had to first find out whether the aircraft performed the pushback or not. And to do so, we came up with a new methodology. There is one on traffic, but we implemented another one where we first defined the areas of an airport where there are such nose-in, push-out stands. And you see that illustrated here with the blue boxes. These are the areas at Zurich Airport, as an example, where there's such stands exist. And then in a second part, we filtered the ground trajectories of a flight, or the ground trajectory of a flight, for all the phases in which the aircraft is moving. And we then checked whether there exists a moving segment which crosses one of the boundaries of these blue boxes. And if such a segment exists, we concluded that this must be the pushback. And you see the result on the left, or some of the results on the left. So the magenta snippets of the trajectory are the pushback parts which we identified, which can have quite fancy shapes indeed at some airports. So knowing that, if the flight was a pushback, we said, okay, start taxi time is the time when pushback ended. And if it was not a pushback, we said, okay, as soon as the flight starts moving, then we conclude that this must be start taxi time. So that's usually flights which are parked on open stands, as you see here, where they can leave the stand with their own engines. So knowing taxi durations, we had to find a way to estimate the fuel consumption of the aircraft, which is also in a three-step process. First, we determined fuel consumption for main engine start and warm up. by considering fixed durations for these processes and by assuming idle fuel flow rates, which we obtained from the ICAO engine emission data bank. Secondly, bless you. Secondly, we found out what the fuel consumption was if the aircraft taxied conventionally, meaning with its own engines. Again, here we basically multiplied the taxi duration with the idle fuel flow values obtained from the ICAO emission data bank. And in the third step, we determined what the fuel consumption was if the flight was towed by an external AGPS. And here we considered APU fuel flow figures because the aircraft has to be supplied by power. So it has to have an engine, an APU running during AGPS taxiing. So that's what we got from ICAO document 9889. So being able to calculate the fuel consumption of a flight, we then applied this procedure for a large number of flights. Indeed, we downloaded trajectories for Zurich Airport covering the period of May 1st to September 30th of this year. And we have now a database of about 57,000 departing aircraft, which only differs by 2.7% of what actually happened according to official data published by the airport. So for all the researchers out there interested in ground trajectories, Zurich Airport is quite well covered on OSN. So that's the go-to place currently if you want to have ground trajectories. In a second step, we then determined on which runways the aircraft took off. As you see, Zurich, we have predominantly runway 28, 32, and 16 in use. And then we checked what the taxi durations are. And you see, as shown on the right in orange, taxi duration to runway 16 is substantially longer than taxi durations to all other runways at the airport, just to keep that in mind for the analysis we did now. So knowing that, we calculated fuel consumption of the flights in 3 different scenarios. And the red one scenario, that's the baseline, that's just status quo. So we assumed nothing changes. We have normal procedures, aircraft taxi out with their own engines. And blue and green indicate now scenarios in which AGPS are in use. And the graph shows on the x-axis the so-called minimum taxi duration, which is, if it's 0, it means that each and every flight, irrespective of its taxi duration, is towed. And for instance, if it's a value of 10, this means only flights with taxi durations of longer than 10 minutes are towed. So that's how you see how AGPS affect the fuel consumption of an airport. And then you see, if we tow each and every flight, we have like a potential or a reduction potential shown on the right of nearly 60%. Whereas if we only consider flights with longer than 10 minutes, it goes down to about 30%. On top of that, we checked what happens if we only consider aircraft taking off on runway 16, since they have longer taxi durations for AGPS usage. And that's what you see in blue. So knowing what the fuel consumption potential is, we realized, well, it might not be super realistic to tow each and every flight. So we did another analysis and asked ourselves, so how does the fuel consumption change if we only provide a certain number of AGPS units or made them available for towing? And in this matter, we assumed that in a 30-minute window, an AGPS unit can only tow 1 single flight. So if we, for instance, have 10 AGPS units available in a 30-minute window, we assume that only the 10 flights with the longest taxi durations are towed, whereas all other flights are taxiing conventionally. And that's how you have to read the graph. And quite interestingly, and that's why I highlighted this fact on the right illustration, is even with quite low numbers of HEPS units available, here 2 units available per 30-minute window, you can achieve quite substantial contribution. So in case that you consider all aircraft for taxiing, we can achieve a reduction potential of 20% by just using 2 HEPS units. And that's quite interesting because we argue that airports, especially large ones, they have an operational reserve at hand of these pushback tugs. So they always have 1 or 2 which they don't use, but they have it at hand if, for instance, delay situations or whatnot requires them. And so if they don't use them as pushback tugs, they could employ them as HEPS units and thereby contribute to a reduction of fuel consumption and a reduction of emissions. So this brings me to the end of this presentation. The key findings are, one should, of course, that's quite obvious, one should tow aircraft which have long taxi durations. These are the large polluters. They stay quite long on the ground. On top of that, airports, even if they don't have like 20 or 30 HEPS units available, that doesn't really matter. Even if they just have 2, use them, because you can contribute quite a lot even with a small number of HEPS units. What has to be said is we assumed we made certain assumptions. For instance, main engine start is fixed and stuff like that. So what we have shown in our paper are maximum values. We expect that in reality, the real reduction potential is lower than what we have shown here. Actually, in the literature, some authors claim or state that the reduction potential is about in the region of 30%, which is doable, and I think that's a realistic number. And this basically brings me back to Flight Path 2050. With HEPS, we cannot achieve emission-free taxiing. That's not possible, just because, for instance, we still will have main engine start, we still will have the warm-up period that we cannot get rid of. But it's a contribution. We can make quite an important contribution towards this goal of having, maybe one day in the future, emission-free taxiing. And to realize this goal, what is needed is practical testing. So airports, airlines, handling agents, now it's the time. Start trying out these procedures, because from an operational point of view, I think there are ways to handle them, but you have to use them. Otherwise, we will never find out what the real reduction potential of HEPS units really is. So this brings me to your opportunities for questions.
Questions in the audience?
Thank you very much for your presentation, quite interesting. Just a minor question, and probably from my ignorance. You say that the airports could use the same HEPS that they use for pushback for making this taxi out. You have considered the speed, because what I feel is that the aircraft moves quite much quickly than when they are moved by these kind of things. I mean, you say that this is better for the longer paths, but in big airport, longer paths could mean something like 15 minutes, even 20 minutes. And if you go half speed, means double the time.
Yeah, you're absolutely right. We have not considered this impact of speed, yes. But you're right, of course. For instance, if you think of Schiphol in Amsterdam, they have this runway which is like out in the greens, with taxi times easily of just 15 minutes taxiing out there at maybe 20 knots or even higher taxi speeds. Yeah, maybe that's not achievable with AGPS units. Yes. Can you estimate the overall energy savings, emission reductions, taking the energy in calculation, taking the energy in the calculation the AGPS itself needs? We have excluded the AGPS at the moment from this calculation, only because we do not have reliable numbers on what they consume in terms of energy. We can argue now, very optimistic, and say, well, we assume that they are all like electricity powered with solar energy, maybe, but that's best case. Of course, they need energy, but we have not counted that in. All right. There are no more questions online, I think.
I have a question.
Sure.
Can you speak to starting and stopping and how does that affect these numbers? So especially like in New York City, we'll see 20 aircraft lined up for takeoff. Does the start, like when you did your fuel burn your calculations, does it take into account that starting and stopping, or is that?
You mean acceleration, deceleration?
Yeah, yes.
No, we have not. There are studies out there which do, actually. There is one study where they have this like a kinetic model where they consider acceleration and deceleration of the aircraft. Yeah.
Okay. Yeah, because I think you know the way you set up your red box, right, for folks who are lining up at places like JFK, literally you'll see 20 aircraft, right, waiting.
Like here.
Yeah, and so they'll have a lot of start and stop. And so I'd be very interested to see if your numbers get even better, right?
Yeah, yeah. I mean, this I haven't mentioned that, but like in reality, we need to find a place where you can disconnect. And the question is, where do you do that? Do you want to do that here on the taxiway? Another idea is to, for instance, use de-icing pads. They are already existing. You can use them. Usually you can have aircraft in parallel to disconnect before then they taxi to the runway and take off.
And then I'll ask one more. Do we see the fuel burn and emissions changing based on weather or other environmental factors, where there are some airports where AGPS might make a lot more sense? Again, where your values might actually be better.
Yeah,
even though you're saying it's optimistic.
The emission model which we used is this ICAO engine emissions data bank, and they just distinguish between, I think it's 4 or 5 different states in which the engine is, being idle, takeoff thrust, and so on and so forth. But they do not consider other variables which affect fuel flow.